Let's go.
Okay. Good afternoon, everyone. So my talk is on Introduction to Higher Form Symmetries. My name is UoE and my thesis supervisor is Theodore Demonte. So this is what I'll be covering today. First, we'll go through a recap, including Noether's theorem, quantum field theory, as well as differential geometry. And then we'll embark on zero-form symmetries. Next, we will generalize to one-form symmetries. We'll talk about them in 2 plus 1 dimensions, and then generalize further to n plus 1 dimensions. And finally, we'll do one case study of Maxwell theory in vacuum. This will include discussions on charge operators in Maxwell theory, as well as Wilson line and 't Hooft operators. So before we even begin, why do we care? Well, higher form symmetries are a form of generalized symmetries, and it's always helpful to have a generalized structure that you can discuss a lot of different structures in. And also, when it comes to higher form symmetries, there are some beautiful topological notions involved. And one more example is just now I mentioned Wilson loops. Wilson loops are a very general structure. It's not a very general structure, but it appears in a variety of contexts. So for example, in condensed matter, and also in QCD, and finally in string theory as well. So let's start with the recap. First, we're going to talk about Noether's theorem. Noether's theorem states that when you have a symmetry transformation, it gives you a conserved quantity. Not only that, it tells you exactly how to construct it via the continuity equation, which is the derivative of the Noether's current, which is equal to 0. To get the conserved quantity, which is the Noether charge, we integrate it over a submanifold, which is a spatial slice in this case, in the case that we are most familiar with. Now, it's important to keep in mind this submanifold picture. Also, as a submanifold, you can think of it as the boundary of the half space on the top or the top or bottom half spaces. So this is another important notion that will be useful for our generalization later. In order to generalize to higher form symmetries properly, we actually have to come up with an alternate derivation of conserved charge. So in your classical Noether's theorem, the derivation will have an infinitesimal parameter, global parameter, right, which is epsilon. But this alternative generalization derivation involves promoting the global parameter to a local parameter. So now it is epsilon x. After integrating by parts, it will give you the continuity equation as well. In particular, this is the form of the first order variation in the action. In the quantum field theory context, the Noether's theorem becomes a word identity. So here, we have the derivative, the Noether's current, acting on some local field operator, and this is in the valid inside the correlation function. On the right-hand side, we have the Dirac delta, as well as the variation in the field operator. Okay, so now we're going to formulate everything in terms of differential geometry. First, I have to introduce to you what is Hodge dual. A Hodge dual basically is a way to assign n forms to become d minus n forms. So in particular, here J is a 1 form, and the Hodge dual of that is a d minus 1 form. So reformulating what we had before, J originally is a 1 form. We take the Hodge dual, and then the continuity equation is written in terms of the exterior derivative of the Hodge dual of the current is equal to 0. And in coordinates, we can see this, right? This del mu, j mu popping up. So we can be sure this is the right way to formulate it. And that is also the reason why we use the Hodge dual instead of the current, of the 1 form current directly. Now, we can move on to the variation in action, the first order variation. We can see that this is the form we had just now in our classical field theory. And now this is the differential geometry perspective reformulation. And now we can see we require this, right? This local nature of the parameter. Otherwise, this will just be 0. And so then it's pointless. Furthermore, again, our charge is the integral of now the Hodge-Dual of the current over a d minus 1 dimensional manifold as we had before. So to tell the story again, actually what we had just now is called the zero form symmetry. We start with a parameter, this epsilon. In differential geometry, this parameter is a zero form because it's a function. And that gives us first our continuity equation via the nodal prescription, and then we have the nodus current. We take the nodus current, we integrate that over a submanifold of d minus 1 dimensions, and finally, via the Ward identity, it acts on the local field operator phi x. Okay. Now we are ready to generalize to the one form case. So we have now, instead of a zero form parameter, we have a one form parameter. And instead of acting on a local operator, we act on a line operator, which is defined on a one-dimensional submanifold, which we call a curve C. And if you're not familiar with a line operator, first, in the local case, we have each point. If you have a function that acts on it, it spits out something, right? For example, if fx is equal to x squared, and in general, each point in Rn, if you have a function act on that, it spits out something. But when it comes to line operators, the function takes in the whole line and it spits out something. So the easiest example is a circumference function. If you have a circumference function acting on a big circle, you get 2 pi big R. If you have a circumference acting on a small circle, then you have 2 pi small r. So notice that it has to be defined on a line. It doesn't make sense for us to talk about circumference of a point. So that is the intuitive understanding of a line operator. Now back to our generalization of one-form symmetry. The details are not important. Just know that all the mechanism we had previously carries through, and in particular, our current is now a two form. So J mu nu, d mu, dx mu, dx mu, and it is antisymmetric in these indices. And therefore, the continuity equation now is written del mu J mu nu equals to 0. And with that, we mentioned just now that now it acts on the line operator. This is the expression. So we have a del mu J mu nu acting on a line operator, which is defined on the submanifold of dimension 1, which is a curve. And the right-hand side, we have some integral over the curve as well. Same, we still have the Dirac delta here. Now, in order to go further, we remind first that the charge, okay, is the integral of the Hodge-Dual on a d minus 1 dimensional submanifold. And so now the charge for a J mu nu, a two-form current, it is integral over a d minus 2 dimensional submanifold. Okay, a simple generalization. Okay, back to our line operator Ward identity. So here, we in fact have a derivative of the Hodge-Dual of the current, and we integrate it over this manifold sigma, omega, and that via Stokes' theorem, okay, we have that it is integral of this star j over some manifold d minus 2 dimension. And how this Stokes' theorem works is that on the left-hand side, we actually have this which is integrating some derivative of some form over some manifold. And the middle section here, we actually integrate that form itself over the boundary. That should be familiar in let's say like 3 dimensions versus 2 dimensions, right? Okay. So on the left hand side now, after integrating this whole expression over this omega, and I'll explain why we are considering omega later. So on the left hand side now, we have a charge operator acting on the line, which is line operator. Okay. Now you can see that the right hand side gets a little bit messy because there's 2 integrals now happening. So to help us understand, let us first look at the 2 plus 1 dimension case. Just a reminder of what we had, and that the charge operator is defined over a d minus 2 dimensional submanifold. In 2 plus 1 dimensions, this d minus 2 is just 1. And so we can consider, let's say, your charge operator can be defined over either an infinitely extended line or a closed curve. So for simplicity, we pick a closed curve, S1. Then this actually gives us a very nice interpretation, which is topological, which is the link of S1 and C. And depending on the nature of C, we can have 2 pictures. So first, if C itself is infinitely extended, then we have such a link. Okay. If C itself is a closed curve, then we actually have what is known as a Hopf link. And in order to understand better what exactly linking means, let us first examine a Hopf link. So there are some very intuitive notions of what linking is. I haven't really defined it yet, but I can think of it as like you can't pull one of them through the other, right? Without it crossing each other. So that is the most intuitive notion. And then also, in the case of a Hopf link, this is a submanifold of dimension 1. This sigma 1 is also a submanifold of dimension 1. So the sum of their dimensions is actually 2, which is 1 less than 3, which is the dimension which they are in. Okay? So this is the idea that helps us generalize to higher dimensions. 2 objects can link if 2 submanifolds can link if the sum of their dimensions is 1 less than the ambient dimension that they are embedded in. Now, we have another perspective, which is what we mentioned just now, involving the omega. So first, we imagine this red circle as the boundary of a red disk. Then we can see how this blue circle, it punctures that red disk, right? And so in this case, if we call the red disk this omega, then the boundary of this omega is our red circle. And so the puncturing of this blue circle through the red disk actually is the same as the link number between the red circle and the blue circle. Right? Kind of makes sense? Okay. Now we are ready to go back and talk about higher form symmetries in m+1 dimensions. So again, on the left hand side, we have the charge operator defined on a d minus 2 dimensional manifold. This is on a this is on the line operator defined on C. And on the right hand side, we have a link between said d minus 2 dimensional submanifold and C. And this link is now the slightly more abstract and harder to imagine, I guess, depending on the dimension case. But the mental picture we should keep in mind is always that of summing the dimensions, and the sum is less than 1 of the ambient dimension. Okay. Before I go on, are there questions about the setup? Okay. Okay. So then we'll go on to one example, which is Maxwell theory without matter. Okay, in Maxwell theory, we have the gauge field A. This is the one form. Then
You've been talking for 15 minutes now.
thank you. And we also have the field strength, which is the derivative, exterior derivative of A. And our Maxwell theory, the action is composed of F wedge the Hodge dual of F. And by the property that two exterior derivatives equals to 0, no matter what form you apply it on, your df, which is equals to d squared A, that is equal to 0. So that gives us our first equation of motion, df equals to 0. And the second equation of motion is that d star f in vacuum happens to also be 0. And we cannot take this for granted. This is not necessarily true without vacuum. So these are in fact two separate equations of motion. So now we have two equations of motion, and remember just now that when you have, this is basically a continuity equation of some sort, and that allows us to define two different charges. So first, the more familiar one, star f, if we integrate that over a G minus 2 dimensional manifold, that is exactly our one form case. Then in fact, we have the electric charge operator. Now, if we integrate star of star f, which is just f, over a two-dimensional submanifold, then this is our magnetic charge operator. So we look at the familiar one-form case first. So if you remember, this f is a two-form, which is exactly like our J mu nu just now in the one-form case, right? And therefore, it must act on a line operator. And this line operator turns out to be the integral of the gauge field over some curve, and then we exponentiate that. So there's a good reason why it has to be this form, right? Just now we mentioned the line operator, it seems like a very generic object, but here, remember that we are in gauge theory. Maxwell theory is a gauge theory, it's a U1 gauge theory. And therefore, first of all, these line operators, if you want them to be physical observables, they must be gauge invariant. And second of all, without matter, it can only be composed of the gauge field A, because it's the only ingredient we had in the theory. Both f and star f, they come from this derivative and then the Hodge dual of A. So that is our Wilson line. This is the famous Wilson line. And to understand the magnetic side, first we try to parallel what we did. So f was just now equals to dA, and we want star f to be equals to d something as well. And so we call this alternate kind of gauge field, is tilde A. And once you have this, then the whole construction carries through. We integrate this tilde A over a d minus 3-dimensional submanifold, and this gives us our magnetic parallel to the Wilson line, which is called the ad hoc operator, defined on a d minus 3-dimensional submanifold. Now you might wonder, we learned about Wilson line and ad hoc operators. What's the physical interpretation? First of all, we already know what the Wilson line is. It actually corresponds to the Aharonov-Bohm effect. Because if you think about it, this tells us what happens when this particle traverses a loop around a vector potential, right? And in the case of 4 dimensions, this d minus 3 becomes 1 as well. So your magnetic component also becomes a line operator. And actually this gives us a probe magnetic monopole work, which is the magnetic monopole equivalent for the Aharonov-Bohm effect. And so to recap today, we covered first Noether's theorem, UoE identities, as well as differential geometry. Then we talked about zero form symmetries, which is what our classical Noether's theorem. And then we generalize that to one form symmetries. And finally, thanks. And so finally, we have example of Maxwell theory in vacuum. So the ending thought I want to leave you with is that this is a very powerful generalized symmetry, and it links very beautifully to a lot of topological notions, which is why we care about such higher order symmetries. Thank you. Yes.
Yeah, you gave us a very nice review of that. I wasn't sure what exactly you did in your project. What was your project?
Oh, it is a review. Yeah.
So your project was a review.
Yeah, due to time constraints, it ended up being that way. Yeah.
What was the original plan?
Oh, there was actually a variant. So here we did Maxwell theory, right? There's some other gauge theory known as BF theory, and then we wanted to calculate something, some specific higher form symmetry inside BF theory.
What is BF theory?
So here we have F, right? That is exactly the same F in BF theory. But BF theory is a topological quantum field theory. So all the constructions are topological. And then B is some background field. Yeah, so the two of them together actually gives you the action. So instead of F and Hodge dual of F, we have F wedge B, the background field. Yeah, it's kind of a toy model, really. It doesn't really describe reality. Yeah.
Okay, thanks.
Thank you.
So you motivated this line integral, but the Wilson line, you also have an exponential and an arithmetical I.
Yeah.
Does that come out with this construction that you should? I mean, why that particular object?
Oh, I'm not sure if that's a good explanation for the I, but the form is. Yeah, I'm not sure if there's off the top of my head I can come up with I, but we know first of all it has to be the integral of a curve, right? Because it's one dimensional, and this curve is either, based on our discussion previously, is either infinitely extended or closed, right? Because otherwise it wouldn't be gauge invariant. The two ends will change when you perform a gauge transformation, and the two ends will not match up, right?
I guess then more specifically, you're not talking about Wilson line, but you're talking about a Wilson loop.
Yeah. Yeah. Okay. Yes, there's a technicality. So yeah, you can in fact, you can always define the lines, but they cannot exist in the Maxwell theory because it is not gauge invariant. But if you want it to be gauge invariant, then you have to define it over infinitely extended line or loop.
The exponential?
The exponential. But if we have the physical interpretation, right, then this Wilson line, if in the Aharonov-Bohm effect, right, it is a phase. So does that kind of answer your question? If we want this to correspond to the Aharonov-Bohm effect, then this whole thing must be a phase. Yeah. So that gives you the exponential at I.
There's a word. So just to recap, because this at least the line integral over the A field.
Yeah.
The loop integral over the A field. So that now corresponds to a symmetry of F mu, or what's the, so I am still a little puzzled about what's this what's the generalized symmetry here?
The generalized symmetry is that normally there is something we actually get these unitary operators from exponentiating these charges.
Right.
Yeah, these charges are the Lie algebra. Okay, then are the unitary operators which act, which, you know, if you have Q here acting on a line, okay, let me go. So from the Watt identity, right, we have this derivative acting on this notice current, and then that acts on the field. And then if we integrate that over manifold, we get Q, right? And then if we exponentiate that, that actually gives us our unitary operator in Hilbert spaces. And so that is what we call the symmetry for this zero form case. And in fact, if we exponentiate this charge over a d minus 2 dimension, that is also in some sense that it is in fact a topological operator, and it is the parallel of symmetry in the zero form case.
Right, but the symmetry is still gauge variance in our case. It's just that there's more invariance than just a charge. Is that a correct interpretation?
I don't think we.
I mean, you started off saying that
Yeah.
you know, let's revisit Noether. We have a symmetry that gives us a charge, and now let's go beyond that, and we have these higher forms. So, but this symmetry is still gauge invariance.
Oh no, it is not. It is not.
Oh, so what is it?
So there are in fact two new symmetries that pop out, which I didn't mention. So first is that this. So first of all, you are right that there is a gauge symmetry to begin with, and then now we also have that, which is U1, right? But now we have two new symmetries, which is U1E cross U1M, which are the one form symmetries in this case.
Maybe it's like another way to phrase Francis' question is typically when I have a symmetry, what I mean by that is I transform something according to a rule. Typically I transform the field and something else remains invariant, for example, the action. So maybe you can help me recall what is the transformation that you're doing and what is staying invariant.
Okay. My understanding is that we think of the zero form symmetries as the unitary operators. So the unitary operator corresponds to some group element which comes about because you exponentiate this Lie algebra, right, which are the charges. So that is how we think about the zero form case, the standard case. And then you generalize this to if you exponentiate these charges, which is again a Lie algebra element, then it produces these unitary operators, which are these topological operators, and that is your one form symmetry.
But I guess, are you saying, the bit I'm kind of missing is, are you saying the action of those unitary operators on the fields leaves the action invariant? That's sort of what I would expect you to say, but I'm not sure it is what you're saying. But something in that language, the action of this thing on the field leaves the action invariant is what I would expect to be a symmetry. And so maybe just missing that step. I mean, I see that you have conserved charges, but I don't see the transformation law completely.
Yeah, I don't think it's we think about it like that, because these charges can only act on the Wilson lines which do not enter the action. So I don't think it actually affects the action in that way. So the way I think about it is because of the, I mean, maybe there are certain parts that I'm not thinking about in the right way, but the way I think about it is that you have topological operators, which is these unitary operators, and then you from that perspective, now you have now by exponentiating the higher form charges, you again have unitary operators, which are topological, and that is how I think about this zero and one form symmetries and higher form symmetries.
Very good.
Okay. No further questions. Thank you again.
Thank you.
Again. Can you real quick, I'll be right back.
Mhm.